So in this video I want to do some background that we're going to need in the case when we get complex conjugate eigenvalues in the auxiliary equation. So complex numbers. We'll start off with the basics. I is equal to the square root of minus 1. So square that. I squared is minus 1. I cubed would be, well, take the I squared equals minus 1 equation and multiply both sides of that by I. You'll get I cubed equals minus I. Do the same thing again. Multiply I cubed equals minus I by I. You get I to the fourth equals 1, and so on. And what do we see as far as a pattern? Well, I see that the odd powered ones, I to the 1, I to the 3, I to the 5, I to the 7 is going to be minus I. I see all the odd powered ones are purely imaginary. I see all the even powered ones. Oh, let's go to the one before I, just I to the 0. I to the 0, count 0 as an even number, is 1. So all the even powered ones, I to the 0, I squared, I to the 4th, I 6, I to the 8, etc., they're all real numbers. And the even powered ones go plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. The odd powered ones, starting at I to the 1, which is I, go plus I, minus I, plus I, minus I. So the odd ones are purely imaginary, the even ones are real, and they both alternate in sign. More facts that we need to bring in. We know the series for E. E is equal to its Maclaurin expansion, 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. Each one of these terms is x to the n divided by n factorial. We also have a Maclaurin expansion for sine. Notice that sine are all the odd powered ones. They alternate in sign, and the power of x matches the factorial on the bottom. And cosine's the even powered ones. This one, we can think of that as x to the 0, then I have x squared, x to the 4th, etc. Again, the exponent matches the factorial on the bottom. So what I need to do is I need to make an equation, Euler's equation, with this. Was the last video when we were doing repeated roots, I asked you to Google math tattoos. If you do it again, Google math tattoos, or let's just see what we got here when we go to math tattoos. This is probably the most common one that shows up. That's e to the pi I plus 1 equals 0. This equation people obviously think are cool enough to etch upon themselves, but you'll also see it on the floor in the Gosnell building on the stairs. So where we're going with this then is, well, we'll eventually, we're not headed here, this e to the power of pi I equals minus 1. We're headed to that, we're headed to an equation that I can then create this equation. Now why do people, just take a second here, why is this so cool? Why do people think this is neat enough to etch on the stairs or themselves? Well, E, that's 2.71 and change, Euler's constant, an irrational transcendental number, is raised to another pi, a more famous irrational transcendental number, times an imaginary number, and I raise a positive number to an exponent and I get a negative number. So that's unusual, and I guess, and it's an equation that has I in it, and E and pi, famous things from math, so it's cool in that regard. Anyway, that's where we're headed. So let's take this e to the x formula, and I'm going to take this e to the x formula, and everywhere there's an x, I'm going to substitute in I times theta, let's say. So e to the x is 1 plus x plus x squared over 2, etc. E to the I theta, it's just everywhere there's an x in here, I'm going to put an I theta. Put an I theta there. put an I theta there. I'll put an I theta there. Now, this is supposed to be I theta all squared, right? These are all of these substitutions in for x are raised to the exponent. And now let's, square both things. This will be both things inside the bracket. That's going to be I squared, which I know is minus 1, times theta squared. This will be I cubed, which I know is minus I, times theta cubed. This will be I to the fourth, which I know is 1, times theta to the fourth, etc. So let's expand, let's clean up those brackets. So when we simplify, we end up getting all the odd-powered ones, theta cubed, theta to the 5, theta to the 1, theta to 7, etc., all have an I in front of them, and all the even-powered ones are real. So let's group first the even ones and then the odd ones. So we have the even-powered ones grouped with the odd-powered ones, and the odd-powered ones all have an I in front of them. So let me factor out that I in front of all of them. And this plus ... is inside. Okay. Oh, now I see why I've got these sine and cos written here. This is just the cosine of theta. It's all the even-powered ones. This, inside the bracket, is the sine of theta. It's all the odd-powered ones. So I can rewrite then, I can rewrite e to the I theta as equal to cosine theta plus I sine theta. This is the equation that I wanted to derive. This is the equation I need. Let's take it and put it back up here. Let's put it underneath that tattooed equation just to see what happens for a second. Well, that works for any theta. If I make theta equal to pi, then I get e to the, so if I'm going to make theta equal to pi in my equation, then I'm going to get e to the pi I is equal to cos pi plus I sine pi, and we know that the sine of pi is 0, so this whole piece disappears. The cos of pi is minus 1, so then I get that tattoo equation. Ta-da. Okay. Less important than defacing your body is developing this equation. So let's take this equation down here because we're going to need to work with it. Now, that's e to the I theta. If I wanted e to the minus I, so I'm going to, or sorry, minus, I'm going to sub in a minus theta everywhere there's a theta in the top equation. So that gives me cos of minus theta and sine of minus theta. And what do I know? Well, I know that cosine is an even function. So if I take the cosine of minus theta, it's the same thing as taking the cosine of theta. It's an even function. Sine is an odd function, so the cos of minus theta is minus the the sine of minus theta is minus the sine of theta. The minus sign pops out. So e to the minus I theta is equal to cos theta minus I sine theta. That means that if I have some kind of a linear combination, which we'll have, of, let's say I'm going to make a linear combination of C1, some constant, times e to the I positive theta plus some other constant times e to the minus I theta, well, I can clean that up. I can clean that up and get, okay, I'm going to have C1 times this and C2 times this. Let's collect on the coses. If I have C1 times this, I'm going to have C1 plus C2 times the cosine of theta plus I times C. Now the signs, I'm going to have a C1 times the sign and a minus C2 times this sign. Factoring out the I, I'm going to get so there's collecting on my sines and coses. Now what do we do? Well, I'm gonna proclaim. Well, it sounds bad when I say I'm going to proclaim. We don't know what these constants are. These are any constants. They will be the constants of integration that we get when we solve a differential equation. There's two of them, so we'd get values for those C1s and C2s by invoking the two of the initial conditions in my differential equation. But since I don't know what these constants are, C1 and C2 and I, C1 and C2, let's group these together then. So in other words, instead of calling it C1 and C2, I'm going to call this, I'm going to say C1 plus C2 is equal to a new constant that I'm calling K1, for lack of a better letter. And I times C1 minus C2, I'm going to call that K2. So I'm just relabeling my constants. Now let's see what we got here. If I had initial conditions, in other words, if I could solve for the C1 and C2, that I could figure out what this expression is, then if I knew C1 and C2 from initial conditions, then I could add them together and subtract them and multiply them by I, etc. So if I knew the C's, I could figure out the K's. That's where I'm getting at. Likewise, if I knew the K's, then I could, two equations, two unknowns, I could figure out the C's. So the C's give me the K's, or the K's give me the C's. They're just different ways of expressing the same information. Another thing that we did here that seems kind of a little bit sweeping under the rug, but we're going to clean it up in a minute. Where did the I go? Well, it looks like C1 and C2, it did add, I renamed that K1. And so C1 plus C2 must be real because I'm assuming that K1 is real. So, okay, C1 plus C2 is real. C1 minus C2 times I, that's real because I just called it C2. So this C1 minus C2 must be purely imaginary, and then when I multiplied that purely imaginary, like, I don't know, 7I or something, times I got a real number, K2. So when I add the C's, I get a real number. When I subtract the C's, I get a purely imaginary number. Can you even do that? Yeah, the C's, C1 and C2 must be complex conjugates of each other. Like C1 is 2 minus 3I and C2 is 2 plus 3I. Then this will work out. How do I know that they are complex conjugates of each other? We'll leave that for later on. You'll see that they are. But for our purposes, if I have a linear combination of e to the I theta and e to the minus I theta, I can express it as a linear combination of cos theta and sine theta. That's all I'm saying right now. That's the piece I want. So I want this. This is the background that I need to solve differential equations that are give me complex conjugate roots. That's true. So what do? Using Euler's formula, we showed that a linear combination of e to the I theta and e to the minus I theta is the same thing as a linear combination of cos theta and sine theta. Now I want to show that a linear combination of cos theta and sine theta, I want to show that a linear combination of cos theta and sine theta is the same thing as a single. I can express that as a single shifted sine function, where a and phi are constants. So in each one of these three cases, we had two constants, c1 and c2, k1 and k2, and here's another two constants, a and phi. A is going to be A for amplitude, phi is a nod to electrical engineering, phi for phase shift. We're shifting this sign back and forth. So I would like to prove that this is the same thing as this. So I need a formula, well, I need our formula from this is a high school formula, right? Sine of A plus B equals sine A cos B cos A sine B. And that's how I learned it in high school back in the day. I need to change this though, because I need to change the way it's expressed, because I've got sine theta and phi. So let's go through here, and to match my high school formula, everywhere there's an A, I want to put a theta, and to match the B, I want to put a phi here. So I'm just changing the letters from my high school formula, but now this sine of A plus phi, that looks like the, well, let's move this over to the other side. That looks like the right-hand side that I want. So now let's match up. Oh, wait, to match up, I got cos phi and sine phi and sine phi. Yeah, so let's move this piece over here so that I'm just trying to match that high school formula. Okay, and now it looks better, I get. Oh, okay, I still got to do more moving around. This sine of phi I'll put over here, so I have cos phi, and this cos of phi I'll move over here. Now everything lines up nice. No, I've got an A in front, so let me multiply this whole equation through by A. Now everything matches up, or at least the two right-hand sides do match. Well, if the two right-hand sides match, then the two left-hand sides match. That means that K2 must equal to A cos phi, and K1 must equal to A sine phi. So I've got these two equations that need to be satisfied to switch from one form to the other. Now we said that the K's and the A's and the phi's are all constants. If these two equations are the same, then K1 has to be equal to A sine phi, and K2 has to equal to A sine phi. So now, in all three cases, we've got two constants, K1, K2, A and phi. Theta is not going to be a constant. I've got K1, K2, and A and phi. Over here, C1 and C2. So theta is not a constant in this case. So here's the relationship where if I had the A and the phi, I could figure out the K1 and K2. Likewise, if I had the K1 and K2, I could figure out the phi's. Notice if I stack those equations as they are, then I'm going to get K1 divided by K2. So stack them like in a fraction is what I mean. So I'm going to get K1 divided by K2. And that should equal to, if I stack these, the A's cancel out, and I end up with tan of phi. So what does that mean? Well, that means that if I had the K's and I needed to figure out the A and the phi, then the phi is just the arctan of K1 over K2. So if I had the K's, I could figure out the phi. Once I have the phi, I can sub it in this equation and figure out the A. Or maybe a more elegant way to do this is notice that sine squared plus cos squared is equal to 1. So if I square both sides of this equation plus square both sides of this equation, I'm going to get k1 squared plus k2 squared is equal to a squared, or a is equal to the square root of k1 squared plus k2 squared. What's the point? If I have the k's, I can get the a and the phi. So if I had the c's, I could get the k's, and if I had the k's, I can get the a and the phi. So any version of the constants, those two constants, in the c's, the k's, or the a and the phi, I could change from one form to the other. How would I get any form of them? Well, they're constants, so I would get them by using the initial conditions. What's our point for this? What's the main point of this video? There's two main points of this video. If I have this expression, I can change it into a linear combination of cos and sine theta, and let's put the main point right here. And this could also be expressed as one shifted sine function. So a linear combination of cos and sine can be written as a shifted single sine function. That phi shifts the sine function left or right, depending on whether it's plus or minus. We're going to use these facts. Let's put that in here. Main point. Too long, didn't read. That's it right here. We're going to use those main points in when we solve differential equations where I have complex conjugate eigenvalues.